Hi guys, my name's Matt, Matthew Harrison, so I'm a third year PhD student and I'm part of the Hetsys CDT and yeah, so welcome to the Computational Toolkit. Today we're going to be looking at an introduction to algorithms, so something a little bit different to the previous videos, but still something that's vitally important. Algorithms is one of those words which you hear of a lot, especially within the computational modeling community, but also if you're outside of that community, you've also probably heard of the term, especially recently in the news, given all of the pandemic modeling that's been happening over the last few years. It's a word that's been used a lot, but although we use it a lot, it's often actually hard to remember what the specific definition is, what actually is an algorithm. So that's what we'll start with today. We'll start with the definition of an algorithm before moving on to some common examples, so 4 or 5 different types of algorithms, and then finally we'll move on to estimating pi. So I'm actually going to do a live demonstration of how we can estimate pi by using a statistical method, a Monte Carlo procedure, and that's going to be implementing an algorithm in a Jupyter notebook. Thanks to Charlotte, I think it was, who's already given us a very good introduction into Jupyter notebooks. So yeah, this extends on that and actually applies it and uses a Jupyter notebook to solve for pi. Okay, so what is an algorithm? So an algorithm is a set of operations to solve a problem by performing calculations, by data processing and/or automated reasoning tasks. So essentially all it's doing is it's solving a problem. So we have a problem that has been defined, and we need to solve that problem by doing one or more of these things: performing calculations, processing data, or some sort of reasoning tasks. And those set of operations are in a specific order. So they're ordered and they execute in that given order, and they're going to solve our problem, hopefully, if we've designed a correct algorithm. Usually they take in an input and they act on these inputs by carrying out these operations, and then usually they're going to give us an output as well, and the output is going to be the solution to our problem. Okay, so an algorithm is the best way to represent the solution of a particular problem in a simple and efficient way. So the key terms here are simple and efficient. We can design horrifically complicated algorithms that solve our problem with thousands of steps, and they're really long and cumbersome. But ideally, we want our algorithms to be as simple and efficient as possible. And I'll come on to what I mean by simple and efficient in a moment. So it's based on both space and time complexity. But first, let's look at analysis and design of algorithms. So analysis of an algorithm predicts the cost of an algorithm in terms of resources and performance. So by resources, I mean usually we're going to be implementing algorithms on computers. So in terms of resources, we're talking about the computational resources that we have, perhaps the amount of time it takes to execute the algorithm on our laptop or a cluster of workstations. And also the performance, so things like how much memory we use and how quickly does it take for it to execute. So there's various different things that we want to analyze. And of course, designing an algorithm is creating that algorithm that uses the minimum amount of time and space. So we want our problem solved as quickly as possible, whilst using the least amount of space. And by space, usually I mean RAM, usually I mean the memory that we require to execute it. Okay, so time and space complexity. So what do I mean by this? I've briefly mentioned it. So time complexity is a function describing the amount of time required to run an algorithm in terms of the size of the input. So let's imagine we've got a data set and we want to calculate the mean and variance of this data set. If we've got only 3 data points, then clearly the time it's going to take to estimate the mean and variance is going to be minimal. We've only got a small amount of data to act on. But if we've got a much larger data set, and maybe 1 million data points, then the time is going to be a much larger problem. And we want to minimize that time as much as possible. Of course, this is a very simple example, and algorithms can be designed to solve much more complicated problems than that, such as density functional theory or molecular dynamics, in which case this is when the time aspect is really important, because these algorithms have hundreds, they have thousands of operations, sometimes millions of operations, and thus we need to minimize that time it takes to run. We don't want code running on our laptops for weeks on end. We don't want to be clogging up a cluster of workstations because our algorithm has been designed inefficiently. So we want to come up with the most efficient algorithm as possible in terms of time. We've also got the space complexity, and the space complexity is the amount of memory our algorithm uses. So again, let's come back to our example. If we've only got 3 data points, then clearly not much memory is going to be used, because we only need to store those 3 data points in memory. If we're only calculating the mean and variance, then those set of instructions aren't going to require much memory. However, if we've got 1 million data points, and if we're calculating something much more complicated than the mean and variance, then memory is potentially a limiting factor. It's an issue that we do really need to focus on. And of course, we're often, it's not just because we want to design great algorithms, often we're actually limited in terms of our resources. So we have a limited time on the cluster of workstations, or we have a limited amount of memory. I mean, my laptop only has 8 gigabytes of memory, so I can't design any algorithm that exceeds that because it will not run. So when we're designing these algorithms, we want to think of these 2 things, time and space. And given that this is only an introduction, I'm going to give a very high-level piece of advice here, and that's that to optimize for both time and space, we want to design an algorithm so that it has the smallest amount of instructions that still solves our problem. So we don't want hundreds of instructions which are redundant or unnecessary or don't add anything. And we want to minimize the amount of instructions, because if we've got less instructions, hopefully it's going to run quicker. And if we've got less instructions, then the amount of memory we're using should also be reduced. Cool. So time complexity, what makes an algorithm fast, and minimal amount of instructions. And space complexity is how much memory is used. Cool. So we've defined what an algorithm is, and we've said how we want to make our algorithms as efficient as possible, but we actually haven't come across any examples yet. So let's look at a simple algorithm, probably the most simple algorithm, just as an example. So imagine we've got a sequence of integers from A1 to AN, and as an output, we want the same sequence of integers, but we want them in a different order. So we want them in an order from smallest to largest. So for example, imagine we have these integers, 8, 12, 5, 9, and 2. These would be our input sequence. And our output, what we want our algorithm to give us, is 2, 5, 8, 9, and 12. So if you're watching this back, have a little think. How would you design an algorithm to do this? Think about how you would break it down into the individual steps to solve this problem. So yeah, feel free to pause the video, and I'll give you the solution in a moment. But before we get to the solution, let's just look at the difference between an algorithm and a pseudocode. So an algorithm is a formal definition with some specific characteristics that describes a process. Okay, so it usually defines the inputs, what inputs we're going to be given. It's also going to define what outputs we want, what we want the algorithm to produce. And it's going to tell us how we're going to transform those inputs into the outputs, i.e. the set of instructions that we need to use to convert those inputs to the outputs. So that's what an algorithm is. It's the definition of those set of instructions. And generally, the word algorithm can be used to describe any high-level task in computer science. Pseudocode is something that's a little bit different, and it can be a little bit wishy-washy. It's a little bit more informal, but all it is it's code that has been written in a human-readable form. So there are hundreds, if not thousands, of programming languages, and they all have ever so slightly different syntax and no one can be an expert in all of these programming languages. So the idea behind pseudocode is to write down the algorithm in a sort of informal code that is completely human readable, and that neglects all of the different syntax between each of the programming languages. So it's human readable code that represents our set of instructions. And the reason I said pseudocode can be a bit wishy-washy is because there's no restriction of styles, there's no standards, and yeah, its only objective is to describe the high-level steps of an algorithm. So depending on who you're writing pseudocode for, you can change it slightly so that it suits them. So there's a big difference between the definition of an algorithm and the pseudocode, which is a human readable form of code that breaks down the algorithm into its individual steps. Okay, so hopefully you've been having a little think about that problem from earlier, how we want to order a sequence of integers. So how would we do that? So our algorithm here is we have an input and an output. So our input is a list L of integers of length n. And our output is a sorted list, L1, containing those integers present in L. Okay, we already know that. But what are the steps? How do we actually break that down? So step one is we want to find the minimum value in list L. So we want to look through our entire list, loop over our entire list of integers, our input, and find the smallest value. And when we find that smallest value, we want to swap it so that it is the first value in our output array, because that is the smallest value. Then we want to look for the second minimum value, and we're going to put that in position 2, and then the third smallest and put that in position 3. So we repeat this process for all of the elements until the entire list is sorted. And once we have that sorted list, there's actually 2 remaining steps, believe it or not. Step 4 is return the sorted list, because we actually want to get the sorted list. We don't just want it to sort the list and keep it for itself. We want it to return that sorted list. And finally, we need to tell our algorithm to stop. When does it stop? Does it keep going forever? Does it run forever? So we need to tell it to stop, which sounds like an obvious thing, but it's actually really important. So let's look at a few different types of algorithms. So here we've got sorting algorithms, searching algorithms, numerical algorithms, pattern algorithms, and graph algorithms. And we'll go into a little bit of detail on what each of these types of algorithms do and where they can be useful. So let's start with sorting algorithms, because that's the one that we're already familiar with. Sorting algorithms are there to rearrange the items of a given list given some criteria. So our criteria was, in our example, that we want to sort our list so that it goes from smallest to largest. But you could define any criteria that you like to sort your given list. And that is what a sorting algorithm can do. The second type of algorithm we're going to look at is searching algorithms. And they deal with finding given values, called a search key, in a given set. So, for example, let's imagine we've got the heights of the entire UK population. And we want to know what percent of people are taller than 6'8", for example. So a searching algorithm would be able to find the number of people that has a height greater than 6'8". That is our search key. And once we know that number of people, we can find the percentage that are taller than 6'8". So a searching algorithm takes an entire set and looks for specific values given a search key. We can then look at pattern algorithms. So pattern algorithms deal with strings, which comprise letters, numbers, and special characters, or bit strings, which comprise zeros and ones, and gene sequences. So they look at evaluating these patterns. We can have strings, maybe AB, 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 or AAB, and it can look for patterns in these strings. So yeah, the go-to application for this is gene sequences. We want to be able to look at different gene sequences for different species, for different animals, and for different individuals, and make comparisons between those 2 patterns. So that's an application of a pattern algorithm. Numerical algorithms is the mathematical side of things. So that's looking at solving equations, solving systems of equations, computing definite integrals, or evaluating functions. So anything sort of mathematical that we need to calculate is a numerical algorithm. That's the real mathsy type stuff. And then finally, we've got graph algorithms, and surprise, surprise, graph algorithms deal with graphs, but perhaps slightly more complicated graphs than you're used to. So graphs can be thought of as a collection of points called vertices, some of which are connected by line segments called edges, and they can be used for modeling a wide variety of applications, including transportation, communication, social and economic networks, project scheduling, or even games. So an example for this, perhaps we can model transport around the UK. So we want to model how the largest cities in the UK are connected by a railway line. So we can have like our nodes of our graph, we can have our vertices for each of the cities, and we can have our line segments, which are our different connections of the railway lines. And we could use that and we could analyze that graph to work out where we need to build new railway lines, for instance. So something similar would have been done as research before the design of HS2 and where HS2 has been designed to be built. Okay, so we know what an algorithm is. We know that we want to optimize it in terms of time and space by making it as simple as possible by using the smallest amount of instructions. And we've also looked at a few examples now, but how can we actually implement algorithms? So in practice, all algorithms are coded, and they can be coded using any programming language, anything that you prefer: Python, C++, Java, PHP, JavaScript, MATLAB, so on, so on, so on, so on. I told you there were thousands of different programming languages, but certainly one of the most popular programming languages is Python. Why is that? Again, have a think. Spend 20 seconds, 30 seconds. Why do you think Python is the most popular programming languages? And if you're not familiar with Python, if it's not something that you're using currently, or perhaps you don't code at all, I will explain now. So Python has lots of positives. One of the main reasons it's so popular is because of how easy it is to understand. It's a really high-level language, so it almost reads like English. If you've never seen Python before, if I gave you some simple Python code, you'd almost certainly be able to read it and understand what's going on. And this fact that it almost reads like the English language makes it incredibly easy to learn and use. There's a really fast learning curve relative to other programming languages, especially relative to lower level languages such as Fortran or C. Python also has amazing libraries. So when you're working on bigger projects, libraries help you save time and cut down the code development time. So imagine you've got a really complicated project. Imagine you've got this huge algorithm, thousands of steps, and part of that algorithm you need to numerically solve an integral. And perhaps you want to use a very simple trapezium rule. Now, of course, you could code up this algorithm yourself. You could code up the trapezium rule. But this takes time. Everything takes time. Even if it's a simple algorithm like the trapezium rule, everything takes time when it adds up. The great plus with Python is that there are hundreds of libraries out there where someone has already written this algorithm for you. Someone has already written the trapezium rule in Python. And so you don't need to write it yourself. So for instance, look at all these packages. These are some of my favorites. So NumPy is a matrix manipulation. So perhaps you're looking for the determinant of a matrix. Your go-to is NumPy. SciPy is much more statistical based. All of your standard statistical methods are in SciPy. Matplotlib is a plotting package. So it would be a real pain to write your own algorithm to generate graphs, whereas Matplotlib has got everything you need: scatter graphs, histograms, bar graphs, line graphs, whatever you want, Matplotlib will have. It's a huge package. Pandas is great for data manipulation. So if you've got large data sets, then Pandas is your go-to. And finally, scikit-learn is more of like a machine learning type library. So it just shows that there are libraries for simple things like matrix manipulation, but there are also quite complex libraries for much more complicated algorithms that you can also use. So something like machine learning, if you're only using it for a specific application, then you don't want to write the entire algorithm for a neural network. It's already been done for you in scikit-learn. Save yourself, save time, and it's more than likely that the algorithm in scikit-learn is going to be better than you could write because there are thousands of developers working on it. Okay, yeah, so this is the thing as well. There's a supportive community. And so Python has tons of documentation, it has guides, it has tutorials, and the developer community is very active. So what I mean by that is each of these packages are open source, and there are thousands of developers always working on them, trying to improve them, and making the algorithms more efficient. And of course, if there's thousands of people, they're going to write a better algorithm than you. So definitely rely heavily on these packages. They're really useful. You don't always have to write your own algorithm in Python. So yeah, the libraries are constantly updated. All right, so to finish off, we're going to look at an interactive example for a Monte Carlo estimation of pi. So this is a relatively simple example, a little bit more complicated than our ordering of a sequence, but still simple nonetheless. And essentially what we have is we have a square grid like this. We have a square, and the square has a side length of 2. So we go from -1 to 1 and -1 to 1, okay? And within that square, we place a circle. And of course, the circle here has a radius of 1. And what we can then do is we can generate random x coordinates. So we can uniformly sample between -1 and 1 to get a random x coordinate. And we can do the same for y, uniformly sample between -1 and 1 for our y coordinate to generate a pair of x and y coordinates. And once we've randomly generated this point, we can plot it on our graph like this. And sometimes our point will be within the circle, and sometimes our point will be outside of the circle. And this is the key thing here. So this fraction, the area of the circle divided by the area of the square, is equal to the total number of points within the circle divided by the total number of points within the square. Okay? And how does this let us estimate pi? Well, we can see in this example that the area of the square, we know what it is. It's a 2 by 2 square, therefore the area is 4. So we have 4 on the bottom of the fraction. And the area of the circle is just simply pi, because the radius of our circle here is r, so the area of our circle is pi. Therefore, pi over 4 is equal to this ratio of the number of points within the circle divided by the number of points within the square. And so if we can count these, and if we can sum these two totals up, then we can estimate what pi over 4 is, and therefore we can estimate what pi is. And I'll show you now in a Jupyter notebook. So as I said before, let's rely on packages. I don't want to write everything myself. I'm going to rely on some packages because I'm using Python. I'll just make this slightly bigger for you. So the first step is to import some packages. I'm going to import matplotlib, which I mentioned earlier, which is my plotting package. And I'm also going to import the package random, which is an inbuilt package which comes with Python, and it lets us randomly sample random numbers. I'm then going to generate a figure. So I'm going to create a figure object because I'm going to plot something later. And I'm going to, as some of my inputs, I'm going to say that I want 1,000 samples. Okay, so I want 1,000 pairs of x and y coordinates. I'm then going to set the number of circle points that I have initially. So at the moment, I haven't sampled any. So there's no points that are within the circle. And there's also no points that are within the square because I haven't sampled yet. And finally, I'll create a placeholder for pi, which is going to be my estimate of pi as I increase my number of samples. I'm then going to use my package. So I'm now in a loop. So this is a loop if you're not familiar with Python. And this is saying for I in range samples, where samples is 1,000, do whatever's in this indent block. So this is a loop, and anything in this indent block is going to happen 1,000 times. So I'm going to sample my x and y coordinates, which is here. I'm going to sample them uniformly using my random package, which I imported. And then I'm going to determine the distance between my point from the origin. And if the distance from the origin is less than or equal to 1, then I can say that my point is within the circle, because the radius of my circle was 1. And of course, all of my points are always going to be also within the square, because my square is from -1 to 1, and I'm generating my x and y coordinates all within that square, -1 to 1. So I can, each time a point is plotted in the circle, I add 1, and each time a point is plotted in the square, which is every time, I also add 1. And then finally, we said that the ratio of the number of points within the circle divided by the number of points in the square is equal to pi over 4. So I just need to simply multiply that ratio by 4 to give me my estimate for pi. I'm then going to store my current estimate for pi in this iteration, and then I'm going to plot my point, the current point that I've just generated. Finally, just to finish off my plot, I'm going to I'm going to plot my circle so that we can visualize what points were in the circle and what points were not. And then I can print as an output my final estimation of pi. Okay, cool. So let's play around with this. So let's first start with a tiny number of points. Let's start with 5 points. And if I run that, then we can see here, obviously I only have 5 points, and we can see that the ratio of points within the circle compared with outside the circle is 4 over 1. Or in fact, 4 over 5, because 4 are within the circle and 5 are within the entire square. And of course, this isn't going to give me a very good estimation of pi. Actually, by chance, this time. It's given me a reasonable estimation of pi, which is 3.2, but it's really not converged because we don't have many points. If I run that again, we get 3.2 again. If we run that again, we get 4. Okay, so you can see that it's really not converged. And so we're going to get an inaccurate estimation of pi with really high uncertainty. However, if I increase my number of samples to 100, then we should get a much more better estimate of pi, because this ratio of points within the circle compared with points in the entire square is going to be more converged. And we can see here now we've got a nice estimation of pi of 3.24, which is really close. And I can push that even further to say 1,000 points. And if we just wait a second, then we can see, okay, 3.124. We're looking really good in terms of our estimation for pi now, because of this ratio is really converged because of the large number of points. We can also see how our estimation of pi converges as we sample each of our points. And we can see here that for a small number of samples, our pi estimate isn't converged. So up to sort of 200, we've got quite inaccurate, and we've got huge fluctuations initially. But then once we get to the higher number of samples, we can see that our estimate for pi is really starting to become converged. So we have much lower uncertainty, and our estimate for pi is likely to be more accurate. So this is just an example of a relatively simple algorithm that solves a problem. The problem was estimate pi, and we've got a finite number of steps. We have an input, which is our number of samples. We have an output, which is our estimation of pi, and we have our set of instructions, which solves our problem. So this is a simple example and shows how you can execute an algorithm in a Jupyter notebook to solve a problem, and that's what we've successfully managed to do. Okay, so that brings us to an end. So we've defined what an algorithm was. An algorithm is a set of operations to solve a problem by performing calculations or data processing or automated reasoning tasks. We then looked at a few examples of algorithms, our very simple ordering example, and a few different types, such as our graph algorithms and our numerical algorithms. We then mentioned how Practically, all algorithms are implemented in a programming language and they're implemented on a computer. And Python is a great starting language if you're new to programming. If not, feel free to use whatever you feel comfortable with. And finally, we did an example whereby we estimated pi by using a Monte Carlo method, which is a slightly more complicated algorithm, but showed how we can use a finite number of instructions and we could convert some inputs into an output. We solved our problem for an estimate of pi. Brilliant. So yeah, thanks for listening. I look forward to the next few talks on the computational toolkit. And yeah, I'll see you guys later. All right, see you later. Bye.